Good morning, 8th graders. So we are starting to now talk about the theory of plate tectonics. So what is going on actually under our feet, not just in Alfred Wegener's ideas and things like that, but rather how is it all actually coming together? So still working with middle school earth science standard 2-3. Basically, by the end of this, you should be able to construct an explanation using evidence to demonstrate how convection currents drive plate tectonics, but also model and explain the theory of plate tectonics using things such as fossils and continental shapes and things like that to support your claim. So make sure you have this in front of you. It is a lot of terminology, but I figured going over terminology this way rather than just saying, hey, have fun, would be a lot easier. So the theory of plate tectonics, let's talk about what it truly is. So it's a theory that Earth is covered in all these rigid plates, 7 major and a bunch of minor. These plates move over the hot plastic-like mantle. So because of convection currents warming up and pushing away, warming up and pushing away, those plates on top have some flexibility in their movements. And then these plates and their movements are what shape our Earth. It's how we look the way that we look today, the amount of mountain ranges that we have, the different sizes of oceans and mid-ocean ridges and all that kind of fun stuff. So that's what the theory is simplistically. Here's what's actually happening. So you have your convection currents, as we have talked about many, many times, and they go around. So they tend to rise in a very similar spot, but then get pushed off to one of the sides to where you create this vent. This is where magma is able to come up through a mid-ocean ridge and start creating new crust. So convection is that hot mantle rising and cooling and just continuous cycle. Now, when you have the plates on top of it, where those convection currents are coming up and then starting to push away, we call our ridge push. This is where ocean plates slide down toward, like pull apart from each other. You're pushing them apart. And then finally, the ridge push actually follows it all the way until you get to that continental crust or another oceanic crust where they're essentially fighting to determine who subducts and who doesn't. To where then, after it meets that continental crust, it starts to be pushed down. But with enough gravity, eventually that slab starts to pull. So if you imagine hanging like a necklace or a chain off the side of a desk, it can kind of sit there for a while, let another link down, things like that. But as soon as there's enough weight underneath, it all just starts going. That's essentially what's happening at the slab pull, where the ocean plate is actually sinking below that continental plate, forcing it to then melt, turn into new mantle and magma to just continue this process. So those are 3 terms that you should probably become very familiar with. So you have your convection currents moving in those circular motions, a ridge push it apart, you're trying to push them away from each other, then finally they get pulled down thanks to gravity. So just another diagram and example to kind of explain what's happening. So the movement within the mantle causes the plates to move. So obviously you can see from here that you have these convection currents forcing movement, at least within the asthenosphere. Okay. Then the hot magma moves up within the mantle. As this magma cools, it comes back down, creating these convection currents. But then the plates are able to move in different directions, depending on where that heat is coming from. So your heat source is pushing up right here. So it forces it to either go to your left or go to your right. Those are your only options. It cannot sink straight down again. But versus you have the cool coming down in this direction. So this is actually where things are coming together, whereas that's spreading apart. And we'll talk about all of those different plate boundaries later within this PowerPoint. But because of all of this movement, you get that ridge push, you get that slab pull, things like that. It's because of these convection currents. I don't know how many times I'm going to say convection currents are the key to all of this, but it truly is. So this is kind of what's happening. You then get really cool geographic, oh my goodness, the words. It's way too early right now. But these geologic features such as trenches and ridges and mountains and all this other kind of fun stuff that we will continue to talk about. But all of these are only able to form because of the movements that are happening. So that is it for a whole group. 5 minutes, well, 6 minutes. In the end, make sure that you remember your champs and we will keep moving forward. So plate tectonics. Earth's surface is made up of a bunch of rigid slabs of rock. We call these our plates. Our lithospheric plates move on top of the asthenosphere. And if you look at this map, it essentially shows you where our major plates are. You get a couple minor ones thrown in there as well. So everywhere where you see this like boundary, that is actually a plate. And this has been determined by many scientists now, mainly our geologic surveys and things like that, to determine where are our plates actually moving and whatnot. So let's talk about the plates before we start talking about their movements. So you have major continental plates. These ones are very large. They tend to hold a majority of our continents, things like that. So let's talk about this. We have the African plate, clearly. You have the Antarctic plate, which holds Antarctica. You have the Eurasian, because remember, Europe and Asia are very much combined. So it's the Eurasian plate, and it's only split up on this because of where the map splits, but it's one big plate. You have the Indo-Australian, so this contains both India and Australia. You have the North American plate, and finally the South American plate. So those are all the major continental plates. Then you have oceanic plates. This is another major one. So you have the Pacific plate, which is actually the largest plate known. You have the Cocos plate, which holds not really much of anything, but underneath Mexico. You have the Philippine plate, which holds the Philippines. The Juan de Fuca, this is one of the smallest plates, but it has a really great impact, especially when it comes to Washington and Oregon. The Nazca plate, which is what's causing a lot of our volcanic mountains in South America. The Scotia plate, which really we didn't even know was there until more recently. But has a major effect. There's quite a few volcanoes on that peninsula of Antarctica. So those are the different plates. A lot of those are minor plates. Some of those are major plates. So let's talk about where these plates meet. So tectonic plate boundaries, these are the things that actually are interesting because you can see why we have certain geologic features. So we have convergent boundaries. So to converge means to come together. C for converge, C for come together. These two plates are moving toward one another. Now there are 3 different ways that these things can move depending on what plates are involved. So you have oceanic to continental, where oceanic submerges because it's much more dense than continental. You have oceanic, which they fight, but one eventually subducts. Very seldom do they both subduct. and then continental to continental. So you have two major land masses fighting one another, coming together, and typically this is where you get mountain ranges. So those are convergent, to come together. Divergent, two plates are moving away from each other. So if you're looking at the plates, they are diving away from each other. So divergent, diving away. Usually this occurs at like our mid-ocean ridges. We do have a couple happening with some continental plates as well. We'll talk about those in a couple slides. So convergent to come together, divergent to dive apart. Then you have transformative. These are two plates just sliding right next to each other. Typically, these fall on what we consider fault lines, such as the San Andreas Fault in California. And we'll talk about why transformative boundaries are different compared to convergent and divergent and what risks and benefits all have. So convergent boundaries, like I said, this is where they are coming together. So two plates coming together can form different natural features. So you either get, like I said, with the continental, you get these mountain ranges coming together. So forming together, you get these ridges, which is where you see quite a bit of like major drop-offs within or trenches where you get these major drop-off from land to bottom of ocean sort of a thing. They essentially look like this, where you have a little bit of land here, but then you don't see land till way down there. And then volcanoes. Because of one plate going under the other, the denser one typically going under the other, you cause a lot of magma to pressurize and get cut off from a magma chamber, but you're still adding more and more things. So typically in this top picture you see, you get all of this pressure built up to where that magma has no other route to go but up, and it's going to take the least, it's going to take the path of least resistance, which typically ends up giving you volcanoes in the middle of the ocean, such as Hawaii. So that's kind of what's going on there. So these are really, really cool. You also get volcanic mountain ranges like the Andes in Chile, where, again, path of least resistance, and for sometimes it's through mountains. So those are convergent boundaries. Again, two plates colliding, typically forming some sort of mountain range or trench or volcano. So coming together, if they're of the same density, like continental and continental to oceanic, typically this is where you get mountain ranges, just because they can't really decide who goes where. Creates giant mountain ranges as the plates collide together. This is the example of the Himalayas in India, butting up to China. They formed these giant mountain ranges. It's the largest mountain range in the world. Convergent subduction boundaries. So we're still talking about two plates coming together, but we need to understand when we have two plates of varying densities. So the super duper dense oceanic plates versus the not so dense continental plates. So the continental plates move, the oceanic plates move under the continental plates, creating a subduction zone. This creates a really deep ocean trench, and where that is let me get my highlighter in green. It is right here, so it's running all along this boundary. And essentially what it is that it is this super deep spot where your continental plate is riding over your oceanic plate, causing this super deep trench. But then it also creates a lot of volcanoes, because again, you have a lot of magma building up here and being cut off from the rest of the asthenosphere. So it has no other option but to go up, and causes many, many volcanoes. Oh, good morning. Sorry, Will woke up. He'll be joining us in a moment. So let's talk about these convergent boundaries. Typically, when this oceanic to continental plate occurs, you create these really cool geologic features, and one of the major ones that we know around the world is the Ring of Fire. So the Ring of Fire is named this way because it is literally this encompassing zone of many, many volcanoes and earthquakes and things like that. So that plus you have great examples of all three of these types of conversion boundaries. So you have oceanic to oceanic, which gives you the Caribbean islands. So these were all once volcanoes. Fantastic, come here, come snuggle me. Okay. Ooh. So that. Then you also have continental to continental, which is where you get the Himalayan mountains. Again, this is from India into like Nepal, and you get very, very large mountain ranges, and they're constantly building still. Then you get oceanic to continental, which is where you get the Andes Mountains that have quite a few volcanoes kind of built into it. You can also see the Aleutian Islands of Alaska are made up of mainly volcanoes. So that's another oceanic to kind of continental, that sort of a thing. Divergent boundaries. This is where two boundaries are moving apart from each other. So these tend to occur at our oceanic and oceanic plates where we see it more often, and this creates mid-ocean ridges. But it can also happen to continental plates, which cause continental rifts. Kind of a cool thing, but also slightly terrifying. This is, again, where plates are splitting apart to create new Earth. So the mid-ocean ridges, obviously you can look at most um, satellite images of our Earth and you can see those very deep lines running through our oceans. So you get the mid-Atlantic ridge. You get oceanic volcanoes, underwater mountain ranges. Good morning. Things like that. But where we have two continental plates splitting apart is actually here at the East African Rift. So you get this little horn that is starting to split apart, and the Red Sea is actually getting larger, and that land is being filled in with ocean the more and more that it splits apart. Again, just another satellite image. You can see the Pacific Ridge and the Atlantic Ridge, but you can see some over in the Indian Ocean and into the Antarctic Ocean, things like that, or the Southern Ocean is what it's now called. Mama. Yes. I want to get my prize though. Okay, I have like 2 more slides. Okay. So then we have transformative boundaries. This is where two plates are sliding right next to each other. Usually it's two continental plates sliding next to each other. This creates a lot of minor earthquakes. You get super major ones at subduction zones. But you get minor earthquakes along transformative boundaries because it's essentially like two plates where if you rub your hands like this next to each other, you can feel your knuckles. If that was like rocks trying to hold them in their places and things like that, that's what causes the, the earthquakes to occur. So we have one here in the United States, the San Andreas Fault, running along basically all of California. Many, many minor earthquakes, but there are also some major earthquakes depending on how much it's trying to move. I know. 2 more. Okay. Okay. Snuggle in. Now, because of plate tectonics, we get these really cool deformations. Basically, how has the plates moving affected what the actual rock strata looks like? So, changing Earth's crust due to stress. So we get compression first, where when you're pushing them together, you are forcing some upward, you're making some compress more, all that kind of stuff. Again, mountain building. You have tension where you're starting to stretch it apart, where in the center it gets really, really thin. This is where you get valleys and things like that. You have folding, which literally looks like a metamorphic rock where it has been bent and folded into itself, creating these kind of weird patterns within the rocks. And then faulting. This is probably one of the bigger ones where you literally take a rock and you split it in half and some kind of jolts down or some jolts up to where you can see where the rock strata would typically line up. So if you look at this first dark shade versus this one. Yep, colors. And all that fun stuff. So that is that. Now, how do we know that all of this is happening now? Well, obviously we've had to have technology that has needed to advance itself throughout time because Alfred Wegener back in 1902 tried to figure all this out, but it wasn't until the 1940s that it really started taking off, and that's because we developed the technologies necessary. So now, thanks to satellite monitoring, GPS systems, things like that, we can actually see all of this movement occurring and measure all of this movement that has been occurring, all that kind of stuff. So that has helped. And to understand that it's only a couple centimeters each year. Like I said, it's the length your fingernails grow within a year. Um, so, yeah, let's play Tectonics. What'd you learn, Will? Yeah, that's how much they're probably going to learn too. Okay, make sure you complete your notes. There is an exit flip that goes along with this today. And we got to get someone a prize because he stayed in his bed all night. Yay, Baba. Okay, thanks, guys.